say a few more things. So until recently, until the end of 2024, I was a postdoc at the Max Planck Institute for Evolutionary Biology at the group Dynamics of Social Behavior. And most of the work that I will be presenting today was work that I did while at the MPI. As of January 2025, I moved to Riken here in Japan, and specifically on the Center for Computer Science, Center for Computer Sciences, RCCS. And here I'm part of the discrete event simulation team. So a few things about our team. So we're all interested, in social behavior. And we use a combination of theoretical tools and computational approaches to derive results. So here actually at the RCCS, we have one of the fastest supercomputers in the world based on 4 different benchmarks. And this is the computer, it's called Fugaku. It's pretty much one floor. So we can use the computer to run large agent-based simulations, either in parallel or like very long-term simulations. So my research in general, relies on software a lot. I am a research software developer, and I'm also one of the main developers of an open source package called Axelrod that allows you to simulate interactions between players when they play, games for a given number of steps. Why I'm saying all this, because actually today's work has nothing to do about computation, so it's mainly going to be theoretical results. There are going to be a little bit of simulations, but nothing was done on the supercomputer. But it's more to say this is what the team is, this is what we're working on, and yes, if you're interested, there are many opportunities to visit us here. But today I'm going to talk about my work on social behavior. I work on social behavior and specifically using game theory and repeated games. I particularly focus a lot on cooperation, understanding cooperation, which is a very puzzling behavior that we see, in nature, in the world around us, in nature, in humans, and even more as life progresses, we're going to see cooperation also between artificial agents or artificial agents and humans. So it is a puzzling behavior, and the many open questions there. So for today's talk, I am going to give a little bit of an introduction and motivation behind our work. And this part, I'm going to say many things that most of you probably already know or already heard like a few times. But still, just in case there's someone who just joined our field, someone who's new to this meeting, please, spare me a few minutes. I will go through some of the basics during that part. For most of the talk, I am going to focus on a recent paper that was published in 2024 on conditional cooperation with longer memory. And then at the end, I will very briefly discuss 2 projects that are currently under review. But there I won't give too much of the details. I'm going to talk about the questions that we ask and some of our results. And that will be the structure of the talk today. So let me start with introduction and motivation. So we're considering a very simple case. So we're considering a game between 2 players, blue and red, the column or the role player, Alice or Bob. And each one of them has 2 options. So they can either cooperate or defect, which we label as C and D. We also assume that the payoffs are symmetric. So actually in this payoff matrix, I'm just showing the payoffs of the role player, of the blue player. So if both cooperate, they get a payoff of R. If both defect, they get a payoff of P. If one cooperates and the other defects, the cooperator gets the sucker's payoff, while the defectors gets the temptation payoff. And in this one-shot game, like what blue needs to decide is, should I cooperate or should I defect? Or should I cooperate with a given probability? So from blue's perspective, it's quite straightforward, right? Like given I'm interacting with red, should I do A, B, or should I do a combination of A and B? I mean, in one-shot games are really well, understood. So regardless of the values of our payoff, like RSTP and, their relationship, we can characterize all the Nash equilibria that they are for these one-shot games. Things become more interesting if we consider that the game is repeated. So now blue and red are just going to play a one-shot game. but we're going to assume that they interact for, let's say, an infinite amount of time. And now here, blue's decision is not very clear. So at turn n+1, blue needs to decide, oh, should I cooperate or should I defect? Should I do a mixture? But how blue will decide this actually depends on the strategy that blue will use. And for here, we're going to assume that blue is going to use a finite memory strategy. So we're going to say that blue will always consider what happened in the last n turns. And then based on that history, is going to make a decision. And these strategies are called memory n strategies. And why we like memory n strategies? Well, for various reasons. And one of them is that they really are, we can describe them very easily by a probability vector. And this is just a vector that says, what is my probability of cooperating given all the possible histories that could have happened? Now, obviously, the number of histories, like possible histories, depends on the memory size, depend on n. And actually, the vector, the size of this vector, actually, you can show that is just 2 to the power of 2n. And then memory n strategies are nice, right? Because we can describe them with a vector. They can become tricky. As we allow for n to increase, as we allow for more memory, the dimensionality of the strategy vector just becomes too large to handle. And it's not just, tractability is not just one of the issues as we allow for n. Another issue is that it's not really easy to interpret them, right? Like we have a memory 4 strategy. There are just so many possible histories. And actually, like interpreting the strategy itself doesn't always make, sense. So what do we do? What does the literature do? Well, we focus, there's a lot of focus on a very extreme case, and that is the case of memory 1. What happens there is, blue would only consider what happened in the previous turn. So they would always keep 1 bit of memory, and then they're just going to react to the previous outcome. And memory 1 strategies are very well studied. And actually, there is a series of very beautiful results in that space. So there is the very famous presentation paper of 2012, where they introduced the zero determinant strategies. But also in the memory 1 space, we actually can characterize all the Nash equilibria that exist within that space. Once we allow for slightly more memory, so even in the case of memory 2, memory 3, such results don't exist. There are some results that, we know that some strategies are Nash strategies in these spaces. But usually what happens is really is one strategy. We say, okay, we take this strategy, it has these properties, we check if it's Nash or not, it is Nash. But it's not really that we have like a characterization of a set of strategies. There is a paper by Stewart and Plotkin that they do get some conditions about whether strategies can sustain cooperation, for example. But then these conditions are not really explicit, right? Like you still need to put numbers into them and like solve some, do some calculations before you can say if a strategy is Nash or not. And what we really wanted was really, can we like get like a really explicit conditions where there a memory, like let's say n strategy is Nash. And this is really the question that motivated our work or has been motivating my work for the past few years. The question is like, can we say anything about Nash equilibria in repeated games for any n? And this is the main question that we also ask in the paper. And the answer is, well, it was published, so spoiler alert, the answer is yes. Yes, we can. And we do this by focusing on a subset of strategies of memory n strategies. So we actually don't do this for memory n, but we do this for reactive-n strategies. What are reactive-n strategies? So memory n strategies would, will look at the previous history and would say, what did I do? What did my co-player, like for example, what did Marta do? And then react to it. Well, reactive strategies would only look at the co-player. So they would only look at, I would look only what like Marta did in the previous turn. You may argue they're a little bit of egocentric strategies, but reactive strategies, we like them for several reasons. So they're very well studied in evolutionary game theory. And the idea is there that, reactive strategies are still like conditioning on what you did. So they still capture this idea of, direct reciprocity. Like I'm going to help you if you help me. So these strategies are still captured by reactive-n. And another reason we like them that is even that if n increases, they're still more interpretable in most cases compared to memory n strategies. So now I would like to walk you through, the several things that we've proved in this paper. But before I do this, let me go through some definitions, because I said a lot of words, and it's just good that we're all on the same page. So the first definition is that of a reactive strategy. So what is a reactive-n strategy? A reactive-n strategy can be defined as a 2 to the n-dimensional vector, P. So every time we're going to see P here from now on, it means that player behaves uses a reactive strategy. And again, it's just a probability vector. But now all the possible histories are not all the possible histories of the game. It's just all the possible histories of my co-player, the minus I. And some examples. So we consider for n equals 1, we have the very famous reactive-1 strategy space set, which is just two probabilities. Will I cooperate if my co-player cooperated in the previous turn? Will I cooperate with a probability PT if my co-player defected in the previous turn? So for reactive-2, now we have 4 possible outcomes in a history of 2 previous turns, whether my co-player cooperated twice, defected twice, or cooperated once, and then we just the sequence between when the cooperation occurred, and then similar for reactive-3. Now here you can again argue that this vector space also increases a lot. It increases exponentially actually, but it is more manageable than memory-n strategies. Some very famous reactive strategies, tit for tat, right? With tit for tat is a strategy that would cooperate if the co-player cooperated in the previous turn, would defect if the co-player defected in the previous turn. Random, a strategy that just at each turn decides whether to cooperate with a probability 0.5. And 2 for 2 tats, which is similar to tit for tat, but it really takes 2 defections for the strategy to kind of like punish you back. From now on, so when I'm going to refer to pure strategies, these are strategies that in their probability vector or the probabilities are either 0 or 1. So any strategy that has probability vectors of only 0s and 1s, we say is pure. Otherwise, we say it's stochastic, right? For examples, tit for tat is a pure strategy, random is a stochastic strategy, 2 for 2 tats is a pure strategy. And the last definition that's actually the most important one is that of a Nash equilibrium. So what is a Nash? What does it mean for P to be a Nash equilibrium in a repeated game? So P is a Nash equilibrium if and only is a best response to itself. And that means that the payoff that P against itself is always going to be greater or equal than what any other strategy can get against P. And when we say any other strategy, we mean any possible deviation towards any other strategy. So in a way, if you want to check if P is an Nash equilibrium, what we need to do is check infinitely many strategies. Now, I know this is not infinitely many people, but this is me trying to draw infinity. So it's a very hard problem. This is not exact. The definition is not, exactly true, because based on the Dyson results, we know that actually we don't need to check against all possible deviations. We only need to check against memory-n deviations. But still, because we're considering stochastic strategies, there's still infinitely many of those. So the first thing that we wanted to do was we wanted to reduce, this space. We wanted to reduce the complexity of this problem. And we did this by deriving a set of technical results, a series of technical results. And the first result is the following. So we established that against a reactive strategy, any feasible payoff can be generated with a self-reactive strategy. What is a self-reactive strategy? So similar to a reactive strategy, a self-reactive only reacts to one part of the history, but in comparison to a reactive strategy, it actually reacts to its own history. So blue is going to look what blue did in order to define the next action at the n+1 route. And what do we mean against reactive strategies? Any feasible payoffs can be generated with a self-reactive strategy. So let me show you a numerical example. So let's assume we have a given reactive-2 strategy for specific values. And then what we want to see is, okay, if it's going to play against a co-player, and we're going to record the payoffs. And that co-player, we're going to sample a few thousand random strategies for that co-player, once from the space of memory 2 strategies, once from the space of reactive 2 strategies, and once from self-reactive 2 strategies. And what we're seeing in this plot is just, yes, select a random strategy for the co-player, calculate our payoffs, and then plot them as a dot. And what we're seeing here is actually, the area of all feasible payoffs for the given reactive 2 strategy that we have chosen. If now we assume that the co-player doesn't play as a memory 2 strategy, but it plays as a reactive 2, we can see that this area is actually not estimated well at all, right? So this area is significantly different and smaller compared to what it should be like. But if we consider self-reactive deviations, we can see that the entire space, the entire area is very well captured. And that is really because our results show that if I'm playing as a reactive strategy and you're playing as a memory n strategy, I can always find a self-reactive strategy for you that will give me exactly the same payoffs. And this might ring a bell, because if you're familiar with the present Dyson work, this is also something similar that they showed. So that was the first thing. Okay, so now we don't need to consider memory n deviations. We need to consider self-reactive deviations. But again, because we're considering stochastic strategies, there are infinitely many of them. And this is when our second result comes in. And what we saw there is actually you don't need to consider any stochastic pure self-reactive strategies. You can actually just consider pure self-reactive strategies. And this is actually a theorem which says that if a reactive strategy P is a Nash equilibrium, if and only if the payoff of P is always greater than equal than what P tilde can receive against P for all pure self-reactive strategies. So what does that mean? So let's go back to blue and red. Blue is playing as a reactive 1 strategy. It means that I only need to check against 4 possible deviations for red. And then if P is playing as a reactive 2 strategy, I only need to check for 16 possible deviations. And then for reactive 3, I only need to check against 256. Obviously, 256 is still like, a large number, but it's better than infinity. And this actually brings me to the third part, which I'm now realizing that the slides are, I need to go forward a little bit, sorry. Which brings me to the third part, which is not here. The third part, the bullet 3 point that should be here is, so we do not only show that you need to go to pure self-reactive strategies, but we also show that we have a more efficient way of calculating payoffs. And what do I mean by that? Is sure, if we want to calculate the payoffs against, blue is playing as a reactive, red is playing as a memory n, what we actually need to do is to create 2 to the 2 times n times 2 to the 2 times 2n transition matrix, and then actually calculate the stationary distribution. We showed no, you don't need to consider memory n, you only need to consider self-reactive n, which is great. But we also showed that actually calculating payoffs can become much simpler, because now all you need to do is calculate a matrix, create a transition matrix that is just 2 to the power of n. So we not only reduce the space, but we also made the payoffs calculation way more efficient. So now we have an algorithm, right? So we say, you want to check if P is reactive, iterate over all the pure self-reactive strategies, calculate the payoffs, and see if you're a Nash or not. And once we had this algorithm, what we want to do, we want to apply it and really characterize some Nash equilibria. So we did this for the most generic case. So we did it for the most generic 2 actions games. But we also did it for a specific game that is called the donation game. And today I'm going to present the results on the donation game. What is a donation game? The donation game is just a specific version of the prisoner's dilemma, where the idea here is If I cooperate, I inflict a cost upon myself. So every time I cooperate, there's a minus C in order to give my co-player a benefit. So every time my co-player cooperates, I get a benefit. Every time I cooperate, I inflict a cost upon myself. And then when both defect, we just get 0. So for the donation game, the first thing that we did was we characterize cooperativeness. And what is cooperativeness? Where is the Nash equilibria that if a strategy plays as a cooperativeness, in the long term, it achieves mutual cooperation, right? So against itself, it gets the mutual cooperation benefit, the mutual cooperation payoff, it gets the B minus C. And what we showed is the following. A reactive-2 strategy is a cooperative Nash if and only if the entries of the strategy satisfy the following conditions. So here PCC needs to be equals to 1, and this is actually what forces it to be a cooperative Nash. So we get the payoff of mutual cooperation, and then the rest of the elements of the strategy just need to satisfy these conditions. And this really creates a space within the 3 dimensions. And if we were to plot it for specific values, this is what it would look like. We can also get defective Nash for a reactive-2 strategy, right? And now here the idea is that your payoff is not that of mutual cooperation, it's that of mutual defection. So for that, we just need to set PDD equals to 0. And then the rest of the elements of the strategy just need to satisfy these 2 conditions. And again, if we were to plot it, this is what it would look like. We did this for reactive-2, but we also did the following for reactive-3. So we got cooperative Nash for reactive-3, and we also got defective Nash for reactive-3 strategies. And I'm obviously not expecting you to look at these conditions and be like, this makes so much sense. But what's quite nice about these conditions, every condition is linear. And we can actually interpret most of them, right? Because it does appear to be a relationship about how many cooperations I have in memory, and then take the average of that. So the conditions themselves are very nice, and are quite easy to interpret. So these are the conditions for the cooperative Nash, and this is the conditions for the defective ones. We can also, so we've seen already this figure, right? Which is, I forgot the legends. So here you should see the PCD, PDC, PDD, right? Because these 3 dimensions become 1 for the cooperative is fixed, this is equals to 1, and the right one, PDD, is equals to 0. One thing that we observe here is that for the specific values that we choose for the benefit and the cost, it does seem that the cooperative Nash, are much more than the defective. And actually, we can estimate the volumes. And this is the first thing that we did. So for a given value given values of cost and benefits, we can calculate how many, the volume of defective Nash and cooperative Nash for different memory sizes. Obviously, what we see is that as we allow for more memory, all the bars decreases. The bar decreases in both cases. And this is actually to be expected. Why it decreases? Because now the strategy space increases, right? So the strategy space is bigger, the conditions still remain. So now you're just there's a smaller place that you occupy in a bigger space within the strategies. But what's quite interesting is as we allow for more memory, the volume of defective Nash drops quite fast. But for cooperative, it stays more stable. And this is actually something we observe even if we vary the other parameters too, So for example, here we're varying the cost. And you can see that for low cost, there would always be more cooperative Nash equilibria compared to defective Nash equilibria, which is not always true. Once the cost goes to 0.5, it changes. But what's interesting is as we allow for more memory, here for the defectives, there's always a significant drop, right? Where for the cooperative, that doesn't seem to happen. And we can also verify this if we take the relative proportion of cooperative Nash as we allow for more memory. So what this seems to indicate is as the strategy space increases, obviously it's harder to land at Nash, cooperative or defective, but it's still more likely that you land up on a cooperative Nash equilibrium compared to a defective one. And this is a pretty cool result. Yes. So then we also saw a series of a few more analytical results, and I'll just like to briefly go through them. So the first extension that we consider, what's okay, everything's good, but what happens with the probability of errors? What are errors? So errors is just like with a given probability I was meant to cooperate and I defected instead. But we don't have biased errors. It's true for both cases. So if you try to cooperate, you will defect with a probability epsilon, E epsilon. And if you're trying to defect, there's also, you will cooperate with a probability epsilon. Errors are nice, but they make things a bit more, they make things more complicated. And why do they make things more complicated? So if we go back to like our Nash definition, so the two things that we need to check. So we have the left-hand side of the condition, and then we have the right-hand side of the condition. And the right-hand side we already simplified as much as we could, right? We went for infinite deviations to a finite set of deviations. And also these are pure deviations. They're deviations towards pure strategies, right? So actually calculating the payoffs here is not such a big problem anymore. We also have an efficient way of calculating payoffs. This is great. We did the best we could. Now, on the left-hand side, when we assume that we want, cooperative or defective Nash, by stating PCC equals, P full cooperation to 1 or P full defection to 0, what becomes really easy is that we know the self-payoff of P, right? It was either going to be B minus C or 0. But once we allow for errors, this is not so easy to calculate anymore. And this is why when we introduce errors, our calculations, our results, it just becomes a bit harder to achieve, get some results, characterize some Nash. But we managed to do it for the donation game. And actually what we showed is that, okay, the probability of errors can vary. And then if we just assume that they're in the case of very extreme errors, so tending to 1, what we can show is that most of the cooperative Nash equilibria that we had already characterized, there still remained approximate Nash equilibria. We say approximate because now the self-payoff is not strictly greater or equal than P, is P plus a small probability delta. So there are approximate Nash equilibria. For a very small error, though, we can see that most of the strategies that we have characterized already as Nash can still sustain Nash. As we allow for more error, obviously they become less and less to the point that they will become a single line. And actually, we do have results about the line, like we can characterize explicitly this line, which is quite cool, and I can talk more about that in the discussion if you're interested. So even for high values of errors, we managed to characterize Nash, cooperative Nash. Now, one thing that it just remains a little bit clear is whether they are the only ones. That we do not know anymore, but these for sure are cooperative Nash equilibria, even in the case of errors. It's pretty cool.
Can I say something?
Please.
I think it needs to be clarified that the original setup also has errors, but to the limit to 0, because then otherwise you cannot define unique self-payoffs. But you always take the limits to 0, but here you consider finite errors. It's and that's one of the reasons why you see this 10 to the minus 7 just coincide almost. Because I mean, since you never talked about opening moves,
yeah.
the left-hand side is not guaranteed to be unique for the kinds of strategies you assume. So there is some errors there also. So I think
no. So yes, Aptash is right, because we're considering pure strategies. The opening move should matter for the payoffs because the stationary distribution is not unique. We actually take all possible like opening moves. So we consider like if a self-reactive can give like mutable stationary distributions, we'll take all of them.
Oh, do you do like a supremum over everything? So that's the way you define pi. Okay, I wanted to be clear about.
Yeah, no, a really good point. But no, we assume that we don't talk about the opening moves. But we assume that, yeah, we iterate over all possible stationary distributions that a self-reactive can give. Like, we're not being smart here. Like, we really iterate over all of them with the opening move. And this is how we get the
No, I
coefficients.
just wanted to clarify what the expression by PP is. Is it a supremum over all stationary distributions, or is it just assuming or picking one stationary distribution through some limit of errors?
Yeah, no, it's, yeah.
But I can read your paper, sorry.
No worries, no worries. Yeah. So that was with errors. Another extension that we consider was, okay, so we're considering reactive strategies, and reactive strategies are a subset of memory n strategies. And then we consider a subset within reactive strategies. And these are reactive counting strategies. Reactive-n counting strategy is a strategy that records how often the call plane has cooperated in the last n rounds. So reactive counting strategies look at the last n moves of the call player, but they don't distinguish where the defection happened. They just count how many defections are in memory. And what's quite cool about reactive counting strategies is that actually we can characterize Nash for any n for the donation game. More specifically, we can show that a reactive-n counting strategy is a cooperative Nash equilibrium if and only if, and we have like our conditions. And we can do also the same for defective Nash equilibria. And it goes back to, again, these conditions are very nice and they're very easy to interpret. So here, as more defections you have in your memory, then you proportionally reduce your probability of cooperating by C over B times n. And then for defective, the more likely you cooperate, will cooperate, you're more likely you are to cooperate. But yes, again, so we can get these very generic expressions for any end. And what's also quite nice is that we can also like interpret this condition. So far what we have done is, okay, so we wanted to characterize Nash equilibria, in higher memory. And we said, okay, let's focus on reactive-n strategies. And by doing this, we can get, a very nice algorithm, and then we can apply it to different cases and different scenarios and get our conditions. But then, the next natural question that comes up is like, okay, now we know that these strategies exist, right? Cooperative Nash equilibrium exists for any memory in the case of reactive strategies, for example. But our question would be, but would a population learned or evolve to play these strategies? So what we did in the later parts of the paper was we ran evolutionary simulations. And there we said, okay, we're going to have a population of players. And then each player is going to start with a given strategy. And then we say, okay, for example, we're going to assume that everyone in the population could play as a reactive-1 strategy. We're going to let the evolutionary process run. What happens at each time step is we choose someone to be a learner, and then they can, either mutate or imitate another member of the population. And we run this for a very long time. And then we say, okay, what is now the average cooperation rate of the population, over, the time steps of the evolutionary process. And also we measure what strategies does the population play over time. And we do this by assuming, okay, everyone in the population plays as a reactive-1 strategy. And then we just repeat when everyone plays as a reactive-2 and everyone plays as a reactive-3 strategy. And these are the results. What you're seeing in the lower panel. So we're changing the cost of cooperation, and we're just measuring the average cooperation rate of the population. And what you can see is that this blue line, which is for the population that has a memory size of 3, it's always higher than a population that has a memory size 2 or memory size 1. So as we allow for more memory, regardless of the value of the cost, the average cooperation rate is higher in the case of n equals 3. Now the question is like, why? And then this is what we're plotting on the upper side of the plot, the upper panel of the plot, which is the abundance of the cooperative Nash strategies. So we measure, how often does the population play as, plays the cooperative Nash strategies. And what we see is actually that this line, the trend of this line really fits the average cooperation rate. So this means that, a population here achieves a very high cooperation rate because they're actually playing these strategies. So they have naturally learned and they stay there for a very long time and they're playing these strategies. And this is even, when memory goes higher, remember, right, the strategy space is higher, like the chances of landing on a cooperative Nash is lower, but still the population goes there and then they just stay there for longer. Yeah, which is pretty cool.
Can I ask, the cost of cooperation, is that relative to the benefit?
It's relative to the cooperation, the cost of cooperation. The benefit here, we have it fixed as 1.
Okay.
If I understood your question correctly. Yeah. We also run for evolutionary simulations with errors, right? And this is what you're saying in the.
Can I ask a follow-up question? So,
Please.
if you can go back one step. So I'm just curious. Maybe I didn't pay enough attention. Is this what's the repetition rate? Is it infinitely repeated?
Yes. So the game is infinitely repeated. And here I am also assuming like low mutation. The game is infinitely repeated.
Okay.
And I'm using a pairwise comparison process. Was that okay?
Yes, sorry.
No. I lost the video, so I can only hear you right now. Yeah, perfect. And then we just run evolutionary simulations again, but now allowing for errors as well. And what we're seeing is again that at least for a very big area, as we allow for higher memory, cooperation is more abundant than in the case of reactive-2 and reactive-1. And here I'm just showing the difference. So obviously, the maximum difference in the cooperation rates are when we consider reactive-3 population compared to reactive-1 populations, right? So it's pretty much the same as we're showing here this line. So blue line has the biggest difference from the orange line, but here we also just allow for the error rates to be positive. And then obviously, we had conditions for reactive-n strategies. We wanted to see, does the population learn these strategies? We also have conditions for counting strategies. So we just now repeat the same process, but now we allow for the population to play either as reactive-1 counting, reactive-2 counting, reactive-3 counting, etc. And we run the same.
Sorry, can I ask a clarificatory question? But
please.
Aren't these strategies a subset of the previous reactive strategies?
Yes.
So how is this different?
Yes, it's more restrictive. I don't know if that makes sense. Yes, they're a subset. So in this case here, you could actually land on a reactive counting strategy and play as a reactive counting strategy. But you can also play as a not.
Okay, so now you count success only if the strategy is reactive counting.
Yes, and the mutants and everyone who's introduced in the population is only counting strategies. So I'm not allowing for reactive.
I see. Okay.
Yeah, that's actually a lovely question. Maybe because then this raises the question, do we ever hear go to a reactive counting strategy? I don't know. But then based on this plot, they're not very successful, so I'm assuming no. But very good question. And what I mean that we don't see much success here, because what we're seeing in the case of reactive counting strategies is that actually it doesn't lead to more cooperation. So all these lines are pretty much on top of each other. And also the abundance of cooperative Nash lines are also pretty much on top of each other. So here in the case of allowing more memory actually doesn't correspond to cooperation rate going higher. It seems that it actually makes no difference.
But I am also very interested in that question because I feel that in a repeated donation game, it seems to me you cannot do any better than just be a counting strategy, even in evolutionary simulations. So,
Whether these results show that you can.
No, but in the full picture, I would want to see how often do you go to reactive counting strategies when you include all strategies.
It's true, but I do have an intuition that it wouldn't be very successful because, like, for these strategies, so one of the tests that I did to understand why is to see how easily they're invaded. And actually, reactive counting strategies, if you allow for mutants that are just reactive, I think they will be invaded quite fast. So I have to check. I don't know from the evolutionary simulations, but I would assume they're also not too successful.
Okay.
Yeah. I can look at the data. So all I'm giving now is an educated guess. It's not a scientifically backed answer. Yeah, and we run the same also for positive errors. And you're seeing again that there's no difference, right? Even when we allow for positive errors, the cooperation rates are pretty much the same across all three simulations. Which itself is a very neat result. Cool. And that brings me to the end of this project. So just to summarize, so the first thing that we did was to kind of create an algorithm to verify whether a given reactive-n strategy is an Nash equilibrium. And here I would just like to give a disclaimer, which is, the first part that, for any memory n strategy, you can find a self-reactive strategy with the same payoff, completely new result. The payoff transformation calculated more efficiently, that's also completely new. But the fact that you had to check for pure self-reactive strategies, that itself was proven with a different method in 2020 by Levinsky in a lovely paper. And I'll talk, I think, a little bit more about that paper later on. Yeah, and then obviously everything else was also completely new. So now we have this algorithm. It is more efficient to calculate best responses, and that's Nash equilibria. So the first thing we did was to apply it in the cases of n equals 2 and n equals 3 and get some conditions for Nash equilibria. And we did this for n equals 2 and n equals 3 for reactive strategies. But for reactive counting strategies, we did it for n given n. We also explored the effects of implementation errors. And then we just ran evolutionary simulations to kind of see if, these now strategies do make a difference. And we saw that they do, because, they allow for more cooperation to evolve as we allow for more memory. And this actually, I only presented some of the simulations we did, but we actually varied several other parameters. And regardless of their values, it was always true that there was higher cooperation in the case of higher memory. Obviously, that was not true in the case of reactive counting strategies. So it does seem that at least in the case of reactive strategies, the sequence of moves when things happen in our stochastic simulations does make a difference. Yeah, so that does bring me to the end of the second project, on the main part of the talk. So for the remaining 10 minutes, I would just like to very briefly talk about some of two works that are currently under review. Hopefully will publish soon. And these works are kind of sequels of the original paper. I can't think of a better word for a sequel right now. Continuation of the original paper. So we're going to take a step back. I'm going to say again, okay, we're going to assume that we have a repeated interaction between two players, infinitely repeated. And then what we've seen so far is, blue kind of like, wants to decide like what is the best I can do against red. And then what we've shown in the case of memory n strategies, actually what Preston Dyson showed, is like, okay, if you're considering the red is playing as a memory n strategy, maybe one question that you could ask is, or should blue play as a memory n plus 100, to kind of like take advantage of red? Preston Dyson said no, because even if you play as a memory n plus 100, I can always find a memory n strategy that will just give you the same payoffs, right? So all the possible payoffs against red can be realized with a memory n strategy. obviously in our case, we said, okay, but now red plays as a reactive strategy. And then obviously press and dice and say, oh, go for memory n. But actually we showed, no, you can even consider self-reactive strategy. And then you can again get all the possible payoffs within that space. And this is just for some subsets of finite memory strategies, right? Like 3 of them: reactive, self-reactive, and obviously the big memory n strategy, the big memory n. But there are many other different subsets within the memory n space. And then, an interesting question comes is like, which of these spaces can I find the smallest space that my payoff, if I've changed to this? So here I changed from a memory n strategy to self-reactive n strategy, and the payoffs remain unchanged for both players. So can I find such spaces given all the possible subset of strategies that red can have? And can I kind of find like the smallest one, right? Because here a self-reactive n, the vector probability is smaller than the case of memory n. And this is actually the work that PhD student Philip has been doing. And he has like a series of results. We already seen the case that I also presented today. If you consider reactive 2, we can see that all the payoffs can be realized if you consider self-reactive 2 deviations. Why such result is important is because we need to know which space should I be looking for deviations, so I don't mistakenly confuse what the best response, not confuse, I mistakenly say, oh, this is the best response, where actually it is not, because I'm considering the wrong space. So in the case of reactive 2, you can find best responses in self-reactive 2, but there are other categories that it would be within the same space. So for example, for memory counting strategies, we can see that you don't need to consider memory n, you just need to consider other memory n counting strategies. And also sometimes the result also depend on the payoff matrix itself. So yeah, Phillips has theoretical results for all this kind of questions. Another project and another question that comes again when considering this interaction between blue and red is, okay, I know that red is playing as a reactive n strategy. A question that I also mentioned before is like, should I remember more? Can I take advantage of red if I'm on like n plus 100? And the answer is no, right? We know that the answer now is no. So when we're looking for best responses to the case of memory n, Levinsky showed that you just need to consider pure memory n strategies. In the case of reactive, us and Levinsky showed that you just need to consider pure self-reactive n strategies. And even though, these are pure, in the how much bits you need in your memory to achieve them is pretty much the same. It's the same space, right? Self-reactive and reactive n, the dimensionality, the bits of memory are the same. So should I remember more than you? Well, the answer is no. You're not going to win much. But we asked a slightly different question, which is, can I afford to remember less than you? And actually, this is a work done by a master student, Francisca, who's also here today, who did her internship with us in the summer. And all the results, is hers. And she's going to actually start her PhD soon with Christian next semester in Linz. So what Francisca showed is like, can I afford to remember less than you? And surprisingly, the answer is yes. It's not yes for any case, but it's yes if the 2 conditions are satisfied. The first one is if the game is additive, and the second one is if the opponent plays a reactive n strategy. And if these conditions are satisfied, then I can afford to remember less than you and still play a best response to you. And this is actually the theorem. So let P be a reactive n strategy, and again, be additive. What is an additive game? The donation game is an additive game. So the payoffs really depend on what you do and what I do, but not so much the interaction of our actions. Then there exists, so if these conditions hold, then there exists a P in the set of pure self-reactive n-1 strategies that is the best response. So in these 3 games, we can show that you can drop 1 bit of memory and you can still play as the best response.
I have a question here. Is it only the case that this like descent from n to n-1 works if, like, it does the opposite work? Like if I'm playing a bit n self-reactive, can I drop down as an opponent to n-1 reactive? Then I can see that a best response dynamics can come down to just memory 1 or something.
Okay, so your question is, if I am I didn't understand your question, I'm sorry.
So here the theorem says that there is a n-1 memory self-reactive best response, right?
Correct.
If my opponent is playing reactive n.
Mm-hmm.
So if my opponent is playing self-reactive n, and is my best response in n-1 reactive?
Yeah, good question. This seems like a very straightforward question, but I still need like a moment to think.
I mean, it's not obvious at all. I mean, it would need proving, but if it's true, then I think they can best response to each other and then come down to memory 1 or something from any n.
Yeah, so what I'm thinking, right? So the idea is that if I play as reactive, I'm only reacting to your history, so the co-player should also react to their history. And if I'm reacting to my own history, then the co-player, so yes, it would hold. Yeah.
Okay.
Yeah. It should, but Francisca, Christian, please unmute and correct me if you think I'm wrong. But I think it holds. Because the idea of why the best response is there, right? Like I am a reactive, so I only look at you. You should also look at you. If I'm only looking at me, you should also look at me, right? And this arguments still hold regarding of who's playing what. And then once you have this, you can prove the pure self-reactive, and then it just happens in the donation game or in additive games that you can also drop a memory. And why the result is cool, just to show some numbers. So again, we want to check if a strategy is, we take a strategy P and we say, okay, is it an Nash equilibria? So what we would normally do is we would check against, and given that n equals 1, we would check, against memory n. So there will be like 16 possible deviations. We should know that there are 4, but actually we can show for the donation game that there are only 2. And then if allow for n equals 2, we reduce from 65,000 to 4. For 3, a number that I don't even know what the number is, to 16. So as we allow for more memory, here we can see that these are just like shifted one position, right? Because it just drops 1 bit of memory. But then, for example, in a normal game, we have characterized strategies up to 3. We could go to 4. I do have a supercomputer. We can do some calculations. But then, we wouldn't have hope to go to n equals 5. But for the donation game, like n equals 5 seems still like achievable. So it's a very cool result. Yeah, and that brings me also at the end of the third part. And then, yeah, just to summarize, so what Philip is currently focused on and what he has shown is, given that you play as a specific strategy from a specific space, can I, move to a different space from, I start, I'm playing memory n, you play as a specific subset of memory n. Can I change my strategy in a set such as our payoff remain unchanged? Yes. And then, Francisca's results really show like, okay, we're looking for best responses. And then and so far everyone has been saying that, you don't need to remember more than me. You just need to remember exactly as much as me, have the same information as me. But she showed no, actually for specific games and specific strategy spaces, you can even remember less. It's a pretty cool result. With that was the end of the presentation. Thank you very much for listening to me today. Thanks, obviously, my collaborators and everyone who has worked on these projects. If you're interested in the paper, one of the papers out. If you're interested in the other papers, they will still be out. So please follow Philip and Francisca. And obviously, thank you very much to the Max Planck and Reagan for funding my research. Thank you very much.
Thank you very much, Nikoleta. I shall now turn off the recording and we can have further questions.